Have you ever been standing in a massive skyscraper lobby, just staring up at the elevator display, wondering how on earth it decides which car to send down for you? Well, it's not magic. It's actually an incredible piece of software engineering. So today, we're going to pull back the curtain on the secret life of the Infinite Tower and see what makes it all tick.
All right, picture this. It's 8:55 a.m. at the Infinite Tower. You, along with hundreds of other people, are pouring into the lobby. Everyone needs to get to their floor, before that 9 a.m. meeting starts. You can just feel the tension in the air. You hit the up button, and now the waiting game begins.
So here's the massive question for any engineer designing one of these buildings. How do you possibly solve this vertical traffic jam? How do you get all these people moving efficiently without creating insane wait times and wasting a whole lot of energy in the process? Well, the answer is a pretty sophisticated dance between logic and code.
To figure this out, we're going to break it down. First, we'll look at the morning traffic jam and see why a simple system just completely fails. Then, we'll meet the system's brain. After that, we'll explore how it picks the smartest path. We'll tackle the skyscraper puzzle. And finally, we'll really appreciate all the unseen complexity that's going on.
Okay, so let's kick things off with what doesn't work. It's really tempting to think of an elevator as just, a box on a string. But that way of thinking, well, it leads to absolute chaos.
I mean, if the system was just a basic first-come, first-served setup, it would be a total nightmare. Just imagine it. The elevator picks someone up going to floor 2. The second the doors close, someone on floor 80 calls it. So it zips all the way up to 80, only to get called right back down to floor 3. It's just wildly inefficient, burning an incredible amount of time and energy.
So to prevent all that chaos, the entire system needs to be run by a single central intelligence. We're just going to call it the brain.
Now, in the world of software design, this is done using something called a design pattern, which is kind of like a ready-made blueprint for solving a common problem. The one they use here is called the Singleton pattern, and you can think of it as one simple, strict rule. There can only be one elevator manager, one brain for the entire building. This is absolutely crucial. It creates a single source of truth, so elevators can't get conflicting commands. It's basically the air traffic controller for the entire elevator squad, making sure everything is perfectly in sync.
Okay, so we've got one brain running the show. But how does it possibly keep track of every single button press, from every floor, from inside every elevator all at once? It's got to have a really smart way of remembering things.
Well, a really clever way they do this is with a special data structure called a tree set. The brain keeps 2 of these lists running at all times, one for all the up requests and another for all the down requests. When you press a button, your floor number just gets added to the correct list. And here's the cool part about a tree set. It automatically keeps all the floors sorted, and, this is key, it automatically gets rid of duplicates. So it doesn't matter how many times you impatiently smash that button, it only gets logged once.
All right, so now the brain has all these requests, and they're all neatly organized. The next job is to figure out the most efficient route for the elevators, and this is where pathfinding algorithms come into play.
The classic approach is something called the scan algorithm. Most people just call it the elevator algorithm. Think of it like a bus route. The elevator starts at the bottom and travels all the way to the very top floor, the end of the line, stopping for people along the way. Then it turns around and does the exact same thing all the way back down. It's predictable, sure, but it's not always the most efficient.
And that brings us to the much smarter version, the look algorithm. Just like its name suggests, the elevator looks ahead to see where the last request in its current direction actually is. So if the building has 100 floors, but the highest up call is only on floor 80, the elevator goes to 80, and then it immediately turns around. It doesn't waste precious time and energy traveling those extra 20 empty floors.
So when you put them side by side, it's pretty clear. Scan is simple, but it's blind. It always goes to the very end. Look is intelligent and efficient. It only goes as far as it actually needs to. It's a perfect example of how a small tweak in logic can save a huge amount of time over thousands of trips every single day. So these principles work great in a normal-sized building, but what happens when you're dealing with a super tall skyscraper with 100 floors or more? The whole problem just gets way, way bigger.
Right, so you just can't have one set of elevators trying to serve all 100+ floors. The wait times would be just awful. The solution is called zoning. The building is basically sliced up vertically into sections. So, for example, one bank of elevators might only handle floors 1 through 20, while another bank handles 21 through 40, and so on up the building. This keeps the trip times for each elevator group nice and short.
And for the really, really tall buildings, you get something even cooler: sky lobbies. Think of it like an airport terminal, but in the sky. Super fast shuttle elevators shoot you express, non-stop, to a transfer floor way up high, maybe on level 60. And from there, you hop on a separate, local elevator that serves the floors in that upper zone. It's really like stacking entire separate buildings on top of one another.
Now, we've talked a lot about making the system fast, making it efficient, but all of that is secondary to the one single rule that overrides everything else: safety.
Every elevator has a very strict weight limit. A pretty common capacity is about 680 kilograms. If the weight sensors in the floor detect that the car is overloaded, the system has one simple, non-negotiable command. The doors will not close, and that elevator is not moving until someone gets off.
And in a real emergency, like a fire or an earthquake, the whole system kicks into safety mode. This is the ultimate override. The brain immediately cancels every passenger request, ignores every floor call, and sends every single elevator straight down to the main lobby, opens its doors, and gets ready for a safe evacuation.
So let's just zoom out for a second and appreciate how all of these different pieces have to fit together perfectly to create this system that, most of the time, we barely even notice.
So you've got this single brain, the Singleton, making sure everything's coordinated. It's using smart memory, like tree sets, to handle all the requests. It's using efficient pathfinding, like the look algorithm, to save time. It scales up to incredible heights using clever designs like zoning and sky lobbies. And it can even switch to a fast-track mode for VIPs. And all of that is wrapped in these fundamental, non-negotiable safety protocols.
And this quote just says it all, really. The next time you step into an elevator, just remember, it is not just a box on a string. It is a finely tuned system performing this incredibly complex dance of software logic, constantly balancing efficiency, fairness, and safety, all to get you where you need to go.
It kind of makes you wonder, doesn't it? If this much hidden intelligence is running inside the walls of a skyscraper, what other everyday things that we completely take for granted are secretly being powered by this kind of brilliant, complex code?